Okay, so the third lecture of Pierre Toledano. Pierre, please go ahead.
Thanks. So today I will focus on a comparison of the measurement that were done. I say were because I stopped more or less at the end of the 80s. But since the end of the 80s, the subject was more or less left aside, and so I don't think there are many. I left not many measurements, but nevertheless, it is important to have a concrete comparison between what the theory can predict and what has been very carefully measured. So before, I just want to draw, let's say, the conclusion about what we said yesterday. The Landau theory predicts rigorously, without any exception, let's say, the symmetry aspect of phase transition, which means the prediction of what phase can appear, their symmetry. This is out of question. No counter example. Now, and so we can, using the Landau theory, we can predict the phase diagram. We can also predict what type of physical property can appear, what is the symmetry of the order parameter. We can predict many things, but we cannot predict, of course, quantitatively the behavior of the physical quantity. We can predict more or less qualitatively, but not quantitatively. And so this was the weak point, let's say, and people from theory of critical phenomena, they went into there to say, and at some moment the Landau theory is wrong. No, it's not wrong. It's almost true, but there is, of course, a weak point, which is the prediction of the quantitative behavior, and especially close to the critical point, which means the critical exponent. And so a lot of work was done after that. Something also that the theory cannot predict is the thermodynamic order. We have seen that depending on the sign of some coefficient, we can have first, second order. And this, of course, the theory cannot predict because the coefficient depend on the geometrical property of the system, of probably other, of the number of the, we already discussed of that, of if we have many secondary order parameter and so on. And so this, of course, also, and so these 2 points, the critical exponent and the thermodynamic order, was the main, let's say, the main subject for the renormalization group approach. So let me, okay, I don't want to repeat things that you know better than me, that the mean field approximation, let's say, the Landau theory is assumed to have the same range of, let's say, of validity than the mean field approximation. And since the mean field approximation can be changed, can be improved when taking into account critical fluctuation, then the renormalization group try to predict more precisely new power laws close to TC, and also to see if they could not predict the thermodynamic order, introducing the concept of stable fixed point. So the critical exponent, let me just remind for people who have no knowledge at all, they are denoted, let's say, beta for the order parameter, gamma minus, something, okay, minus gamma for the susceptibility, and alpha for the specific heat. So in the renormalization group at variance with the Landau theory, where the critical exponents are, let's say, unique, whatever be the dimensionality of the order parameter, the interaction, we have only one type of critical exponent, which is, of course, a weak point. And so here, the renormalization group approach, let's say, showed that the critical exponent depend on the spatial dimension of the system. In general, let's say, for people with good sense, it's 3, but of course, we have some reduction, which can be possible depending on the type of mechanism. The number of order parameter component, the anisotropies of the order parameter, which are related to the anisotropy of the crystal, but in an indirect way, and also sometimes a bit complex, and the range of the anisotropy of the interaction inducing the phase transition. So there are actually, as I could see, 4 classes of structural transition which have been mainly analyzed. So-called elastic phase transition. In reality, it's a part of the elastic transition. The elastic, let's call them in some modern way, the proper ferroelastics, which are the ferroelastics where the order parameter is the strain or has the same symmetry as the strain. Now, you have a second category of phase transition where the order parameter is smaller or equal to 3. We will come back on that a bit later, of dimensionality 3 and short range forces. Here we have exact result, but they do not solve the problem of the critical exponent, as we will see. And uniaxial ferroelectrics, there are more or less, we have really beautiful phase transition with second order phase transition in this class of transition, uniaxial, for example, TGS, and so on. We have a list of cases which are really pure with a nice second order phase transition, but unfortunately, the results are not at the level. And finally, the transition with n larger than 4, because here the work was not completely done, and it took some time before we had some result, case by case, because you have many possibilities. And let me begin by a comparison about elastic phase transition. So it mainly, I say mainly because it can also include, for example, ferroelastic coupled to ferroelectrics, but mainly it's the strain play an essential role, and it has a specific critical behavior because first we have a strong anisotropy of the elastic instability, and secondly the divergence of the fluctuations are confined in limited region of the reciprocal space, either in specific direction, and the tradition wanted to denote this case m equal 1, or in planes of the reciprocal space m equal 2. So for m equal 1 and d equal 3, as we will see in the next slide, it really fits very well with the classical, with mean field Landau theory critical exponent. Of course, calculations show that when you reduce the dimensionality, then and also some experimental examples show that it does not fit with the, let's say, Landau mean field classical exponent. I don't know why when I turn my head, okay, I saw I would stay like that. For n equal 2 and d equal 3, there has been some works showing that you had to include, how to say, logarithmic correction to the classical results. So let's go to the next slide. Here,
Pierre, you don't give any pictures, but the example that you considered yesterday, where there was this atom moving in one direction in the center, it was not ferroelastic. What was that?
no, it was purely ferroelectric.
It was ferroelectric. Okay, okay. So
Yes.
ferroelastic means you just have some direction of your
Yes,
radius which changes, but
the rule for ferroelasticity is that you have to change the form of the crystal, which means to go from one, let's say, one Bravais lattice to another. I mean, cubic to tetragonal, cubic to orthorhombic. If you stay in the cubic system, of course, it doesn't work because you have cubes and no deformation. If you stay in the tetragonal system, you don't have. So you need to change of crystalline system. All right. But of course, the hexagonal and rhomboidal system is considered as only one system because the crystal has more or less the same form.
okay.
Okay, so I have two slides in reality which I want to show before going to the comments. The first one is for the beta exponent, and the next one is for the gamma exponent. We don't have some, let's say, systematic studies for the alpha exponent. So here I have listed on the left-hand column the material which have been very well investigated. I indicated the let's say experimental techniques which are really well adapted for the measurement. So the numbers that we have are really quite, let's say, reliable. And on the left hand, people at that time were doing things very carefully. They have measured the extension of the critical region. So we have also some data. Here I have separated the case of ferroelectric, ferroelastic. There are two examples, and m equal 2 also separated. So what can we say? What can we say? First, we have an excellent agreement with the classical exponent. It's really very nice, 0.5. It's exactly what Binfield or Landau predicts. And also, there is a coherent values. This is not so common between beta and gamma measurement. I just show again gamma. We have one, really one plus or minus something. Okay, sometimes it's not the case, but I will come back on when it doesn't work. What can the power law remain valid from 10⁻³ to 4 to 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ the critical region. Now, out of this critical region, there has been many proposals to fit. And in reality, what people have shown is that it fits when with Landau polynomial higher than 4. You have to go to, let's say, to add some terms to really fit well when you go far from, because of course the order parameter is larger, so you have to take into account higher degree terms. Now I go to the other sequence of comments, but there are of course some exceptions to the global agreement, I mean, inside the critical region and outside. For example, dy v04, which is here, it fits with the classical exponent only below 10 minus 3. As soon as you go, and so it's quite quite narrow, you begin to have non-classical power laws. Now to reconcile the fact that it doesn't work inside the critical region and outside, people have made some proposal. One of the proposal was to say that the elastic behavior, so the one which fits, it dominates in a small interval which can be, let's say, predicted of the order of W divided by K, the Boltzmann constant, where W is the elastic energy of one unit cell, and which coincide with the saturation value of the spontaneous strain. And so if there is another slide to show that this is the extension of the elastic domain. It goes, as you see, from 3 degrees to almost 350 degrees. So it's larger than 100 degrees for most material, justifying a classical behavior in the total interval of temperature. But this is not true, of course, always. There are 3 materials at least where there is a change in the critical regime. Now, comment for n equal 2. I come back to the preceding slides. You see that for n equal 2, it doesn't work for the coefficient beta. You get, let's say, half more or less of the predicted value. And
actually, Pierre, I don't understand, like, I don't picture very well. What does it mean m equal 2 geometrically? I have no idea.
Fluctuation along, well, from the point of view of the strain, it means that, you see, you have different type of deformation. You have uniaxial deformation, let's say, and you have bidimensional deformation when, for example, you showed me yesterday when I showed the cubic deformation, the coupling, you have 2 types of deformation, one shear strain and one tensile strain. So let's say more or less tensile. Yeah.
So for example, something like tetragonal to monoclinic, it would be m equal 2?
No, it's not related to the symmetry. It's related to the form of the strain. If you have tensile strain, then it's more or less uniaxial in direct and in the reciprocal space. But if you have also shear strain in the same time, then you necessarily have some planes.
Okay.
You see, it's a plane which is deformed. For example, if you go from, let's say, tetragonal to orthorhombic, then it's clear that both of them have 90-degree angles. Huh? So here you don't need a shear strain. But if you go from orthorhombic to effectively monoclinic, then you will need a shear strain because one of the plane will be deformed. But you have to see, of course, the n equal 1 and n equal 2 in also the reciprocal space, because fluctuations are in the reciprocal space, let's say. And so this is the difference.
Okay.
So for m equal 2, you see, it's, let's say, a bit controversial. For KCN, it works. But for the other one, you have, it doesn't work. It doesn't work at all. And for beta, both of them do not fit. Okay, so it means that even for these proper ferroelastics, it works, but you need to have some specific type of deformation. But it works well. At least we have something which works. That works.
No, but how does it work? I mean, theoretically, this is puzzling because you say if it's 0.5, it works, but theoretically, it's puzzling because we know that fluctuations should play a role.
Okay. This is
it works for you, but for us, it's like doesn't work.
Okay. So try
Do
to
you have
find
any
one.
comment? Why is in this case
But
fluctuation?
these are experimental results, very carefully obtained using several techniques.
Okay,
So,
but as a theorist, why in this case fluctuations don't seem to play a role? What's your opinion?
what? Sorry, can you repeat?
I don't question experimental results. Certainly they're correct, but there has to exist some explanation, theoretical explanation, maybe having to do with that this the interactions are long range or something like that.
Explanation, but it's
Yeah.
I don't want to today. I wanted that my talk looks very concrete and with facts.
Okay.
But if I can now speculate, you see, in reality, all ferroelastics, they are also anti-ferroelectrics. And anti-ferro, and this may be the key for the explanation. But I don't want to enter that because it's a personal theory which I began to publish about ferroelastic. Because you see, I never liked this, let's say, this tensorial classification of structural phase transition. I believe that as for, let's say, magnetic phase transition, where you have ferromagnets and anti-ferromagnets, in structural transition, you have ferroelectrics and anti-ferroelectric. But of course, anti-ferroelectric, it's very difficult to evidence experimentally. It's only some, let's say, macroscopic thing which define anti-ferroelectricity, which is, for example, a double hysteresis loop and things like that. But at the microscopic level, you cannot see the dipole. You can see the spins because of neutron diffraction, but you cannot see the dipoles. So it's always some, let's say, some struggling between people to say, is it anti-ferroelectric or not? So my feeling is that it is. We can discuss another time of that. I think it's too early to give an explanation.
Okay.
So let's continue. All right. Now, so there are incomplete results for n equal 2, for beta differs, gamma is good. We can also, there has been some prediction about KDP, about also that it could be, it was some time fashioned to show some, let's say, logarithmic correction after the work of Larkin and Khmelnytsky. My wife asked me to repeat twice this name, not to be incorrect, Khmelnytsky. Everybody began to find some logarithmic correction, but in reality, it's so complicated way to confirm this logarithmic correction that really you need to be very, very favorable to this explanation to accept it. So in reality, we don't know for n equal to why it doesn't work. Now, let's go to a more firm state, which is non-classical structural transition. Non-classical means we have short range interaction. And it concerns, if we want to use some other vocabulary, it concerns improper ferroelastic, improper ferroelectric. It means that the order parameter is not a macroscopic quantity. It's some short range mechanism, displacement and so on. And here it's interesting because everybody accepted the idea that in reality the crystal anisotropy are erased by the fluctuation, and then the critical exponents depend almost exclusively on the number of components of the order parameter. And so it has been determined, as it depends only on the number of components, it's the well-known work by, how to say, Zinjustin, Brezin, who calculated once forever with a precision which is impossible to reach at the experimental level, but they calculated once forever the critical exponent for alpha, beta, and gamma. And you see that what they find is that for alpha, it's around 0, but not, it can be a bit more for unidimensional order parameter, a bit less for the second with n equal 2 or 3. Above 3, it doesn't work, this argument of anisotropy erased by fluctuation. So we remain only below 3. The beta, we see that it's smaller, and the gamma is larger. This is the result. How? Okay, it does not apply only to improper ferroelectric and ferroelastic. I know that it also applies to piezoelectrics. I mean, a number of phase transition governed by short range order. The problem is that in this class, as you go from proper to improper, most of the transition, the density of first order phase transition become much larger. And so we have many first order transition, but a few second order transition, but we still have some, mainly in the perovskite family, which means when the parent phase is this cubic PM3/n phase, but not only. And so here I have indicated the result which have been obtained. I will not speak about strontium titanate because let's say tomorrow we will have a talk by Amnon Haroni about strontium titanate, and I don't want to give, let's say, my opinion about it. So we see that the theory gives more or less 0 for alpha, and you see what is the result. So for the alpha exponent, the experimental data, I did not note all the experimental measurement, but the experimental, we don't have, of course, experimental measurement for gamma, because it's not easy to know when you have a short range mechanism, what is the conjugated field to this mechanism. So we cannot determine, we cannot measure well the gamma exponent, but beta and alpha, of course, we can. And so if—
Yeah, can you explain why do you know that in this case there was, why do you call these things short range while the previous case, I imagine you classify as long range? What allows you to make such a conclusion? Because for us, it's very important, this classification to short range versus long range.
I must tell you that it's not my denomination. It's what you find in all the paper at the time of the renormalization group. Or it was more or less, let's say, accepted, this denomination. But then I can have, I can understand that elastic interaction have a long range. This I can understand. And I can also understand that the Coulomb interaction, for example, for proper ferroelectric, have a long range interaction. But if you have a mechanism which is only a mechanism of contact, of turning of some atoms, of, let's say, displacement, this mechanism is, of course, not long range, it is short range. This is how I see that, but perhaps there is a more, let's say, elaborated way to say that.
Okay.
Okay? So we see that the alpha exponent is always larger, except for strontium titanate, where it's more or less of the same order that what is predicted theoretically. concerning the beta exponent, it's always smaller, except for strontium titanate. Fits more or less well. Strontium titanate is a typical improper ferroelastic. All right. So some comments. So as I said, alpha value much higher, except SR strontium titanate, and beta always smaller except this case. Now there have been some explanation proposed for this difference between the experimental and the theoretical result. First explanation, which seems to me a bit easy, but it has been proposed many times, is that we are not far from a tricritical regime. You know, at the critical point, the tricritical point is defined by the fact that the fourth degree coefficient becomes 0, and so you have to take into account the 6th degree coefficient. So if you minimize, then you find that your coefficient, that let's say beta, varies as with the power not 1/2 but 1/4. And so when you go near to this tricritical point, of course you go from 1/2 to 1/4, and so you have a smaller exponent. Second possibility that was proposed was the fact that we have asymptotical regime, which is realized in a very, at some moment even people were saying that the critical region could never be observed really experimentally. So you have this asymptotical critical regime can be observed only very close, 10⁻⁴, so you cannot really reach it, to the phase transition, so not accessible to the measurement. So all what you measure, it has nothing to do with the real critical behavior. Okay, but this is just, yes? I am sure, yes, but I don't.
Can you please repeat the question?
He asked me if there had, let's say numerical of these different possibilities to understand why we were not in the good with the, let's say, good numbers, why the beta exponent was generally smaller than what was expected by the renormalization group. I am sure there has been, let's say, numerical simulation is at present at least one of the most simulations, so I am sure that there has been. Now, there is a third interpretation, which is maybe interesting, is that you have an intermediate critical regime which corresponds to reduction of the effective dimension of the system, going from 3D to 2D, due to secondary interaction competing with the interaction which determine the critical regime. All these explanations say nothing about the other coefficient alpha, and also because why it doesn't work. So it's really some possibility to explain why it doesn't work for beta. Alpha was aside from all the, I don't know why it stops from time to time. All right, let's try to go to the end. Now, at some moment, because it's uniaxial ferroelectrics are full of second-order phase transition. They have been also extremely well studied, so we know that we have really second-order phase transition. And so people try to predict something. So to predict why for uniaxial ferroelectric, but unfortunately, we don't have many results. Only TGS, only another material which is, trisarcosine calcium chloride. There were attempts to adjust the obtained result with some logarithmic correction. But it was my feeling, I can only give a feeling, is that first, it appears that the correction, logarithmic correction, are very large compared to the value. So it's not really correction, it's change. And secondly, they assume also many things. They assume a change in the critical regime. They assume this, they assume that. I mean, it's not a straightforward interpretation. So I cannot say much more about it, but it's a pity because these systems are really beautiful from the point of view of second-order transition, and also the fact that we know it is Coulomb interaction there because it's purely ferroelectrics. Now, for n larger than 4. So for n larger n, it is, let's say, there is some consensus admit that the crystalline anisotropy play then an essential role, and so that the theoretical prediction are not unique, let's say uniform, but we did not have here. I noted the two main examples, which are dioxide niobium and biphenyl C12H10, where there has been a measurement of critical exponent. But in this direction, which started a bit late, because we know let's say, people began to work in calculating a stable fixed point and all this story after 1985, and it stopped at the end of the 80s. So we don't have so many calculations, and we don't have so many measurements, because of course you measure if you know what you have to find, and this was not the case for n larger than 4. By contrast, there were many articles trying to show that the presence or the absence of a stable fixed point allows, let's say, predicting if the transition is first order or second order, which is effectively, we need some prediction of this type, which is lacking in the Landau theory. Here I want just to come back a little bit about the prediction of the thermodynamic order. We have a very good criteria in the Landau theory, which is the fact that we have a cubic term in the free energy, so-called symmetry cube criteria. And this is really very reliable criteria, which ensure the fact is first order, but it can be very weakly first order, but it is first order. Now, also what we know, I'm sorry to come back on that, I know that you don't like too much this argument, the fact that the secondary order parameter can of course change the sign of the 4th degree coefficient and push the transition to have 6th degree term with a negative 4th degree term, yes, and so this would be also, let's say, a possibility to understand why a transition, if you have secondary, very large secondary order parameter, which can really change the sign of the fourth degree coefficient. And also, I would like to say, because let's say Slava asked me to look in the Larkin-Pekin prediction of going from second order to first order under compressibility or interaction. It's the same argument then, let's say it's the influence of elastic property on transition, which is not of elastic origin. In their paper, I think they examine TGS, and so I think it's the same. Not exactly, because they do, of course, very nice calculation, and they reach some logarithmic correction, very precise. So I don't say nothing bad about this very good paper, but only to say that in essence, it is the same argument than to mention that secondary elastic order parameter can affect the critical behavior. So let's say the renormalization group at some moment, since it was not easy to have people measuring critical exponent, most of the paper were mainly focusing on, let's say, fluctuation induced first order phase transition in absence of stable fixed point in the flow of Hamiltonian, or because the fixed point is not, let's say, accessible. So the problem is of interest only for n larger than 4, because for n smaller or equal to 4, it does, I mean, we always have a fixed point, which is the, let's say, isotropic fixed point, and so let's say this criterion that in absence of stable fixed point doesn't work below n equals 3, and below n equals 3 we have precisely most of the structural phase transition. I mean, the largest number of structural transition are below n equals 3, and they are either first or second order, and we would like to know why. So it doesn't work for n smaller than 3, but for n larger than 3, most of the paper were devoted to that. There was a possible comparison with experiment, which has been done in a number of materials. So here I have listed the material which I could find with n equal 4 or n equal 6, number of order parameter component, the order of the transition, and the fact that we have, because it has been with, except to some interrogative point, it has been measured, it has been calculated, and also in the last column, I have noted, because it could have some importance, but in reality it doesn't have, if the transition, the order parameter is active. Active means that it fulfills the Landau criterion, cubic term, no cubic term, and the Lifshitz condition. So the active means here that it satisfies the Lifshitz criterion and the Landau criterion. So here I have noted when it does not, on the last column down, when it does not, but I think here the Lifshitz, it appears that the Lifshitz condition has no importance. I mean, if you go to an incommensurate phase via a second order phase transition, is in reality the same critical behavior, more or less, even if there has been some work showing that it was not exactly the same critical behavior. I think it's not so important that you have a slight, let's say, incommensurability of the lattice and not a strict periodicity.
So just to make sure, in cases where you say Lifshitz criteria is not satisfied, it means that all those transitions are incommensurate.
No, it would be too simple. Let's say the field of incommensurate phase is quite vast. So let me only here summarize. At the beginning, people try to understand why, especially because the K, you remember yesterday I said that Lifshitz condition select a number of points in the Brillouin zone, the center, and some high symmetry point on the surface, which fulfill this criterion. Okay? All right. But now, people who work began to find that in many times, the wave vector was temperature dependent, began to move in the Brillouin zone. You can even find it at completely irrational value. So they began to say, okay, here is not fulfilled. Then it opens some new mathematical field, because here you have to minimize integral, since you have to introduce in the free energy some, let's say, gradient term with also Ginzburg term, the second degree of the derivative. And then people began to how to solve by the Euler-Lagrange equation such type of integral. So it was a big fashion, I would say, at the beginning between the 70s and the 80s about incommensurate phase. Also, people began to find more and more incommensurate phase. Then what theoretically followed? First, the first one were interpreted by the fact that the Lifshitz condition was not fulfilled. So you had a Lifshitz invariant, okay. Then people found incommensurate phase without Lifshitz invariant, even in system where the Lifshitz condition was satisfied. And so they began to invent the concept of Lifshitz type invariant, something which looks as a Lifshitz invariant, but which is not the Lifshitz invariant at a high symmetry point of the Brillouin zone. Okay, what I can say only now, you have many incommensurate phase. I mean, the field of incommensurate phase developed because people with X-ray now, they are much more, let's say, accurate than they were before. Also, the field of quasi-crystals push people to find, let's say, incommensurability and non-strict strict periodicity in many crystals. And so, to answer now to your question, when all incommensurate phase do not necessarily, let's say, violate the Lifshitz condition, but the Lifshitz condition is one possible explanation for the existence of, let's say, it's clear that the order parameter varies slightly because you don't have a strict commensurability. And so, yes, the Lifshitz condition is a possible interpretation, formal, phenomenological interpretation of incommensurate phase. What is sure is that you have a lot of very nice second-order phase transition to incommensurate phase. Now, here you have, of course, Landau. I wanted to put some Landau examples because it's always first order, and that, of course, nobody, only one case here, I don't know why it was measured here. It's first order, it doesn't fulfill, I think the person who measured that did not know that the Landau condition was not fulfilled, but sorry, it's not this one, it's this one. There is no stable fixed point, but of course, you have a cubic term. All right, but now all the other one, what are the commands that we can do? So in VO2, in V3SI, in NB3SN, in BAMNF4, the transitions are first order in agreement with the absence of stable fixed point in the Hamilton. Conversely, in NBO2, barium sodium niobate, biphenyl, we have a second order transition consistent with the presence of a stable fixed point. So everything looks well here, but But in CDNO3 twice, CDSN SA2, they are first order despite the presence of a stable fixed point. Okay, this we can understand it. Not the phase fixed point is not, let's say, accessible. But conversely, in the boracite, nickel iodine boracite, and I'm happy to present this because I looked for it. It has a second order transition despite the fact that you don't have a stable fixed point. Okay, here you have a beautiful second order phase transition and no stable fixed point. Also,
this is the case. This is the most interesting for us case because this is a puzzle.
And it was I went to Russia, discuss with Dialoginsky about this material. You see, it's some, I come back to the beginning. And so there is also another case which is interesting. It's the cubic orthorhombic 6-dimensional order parameter in sodalite, aluminate sodalites, family of compounds, the sodalite. It exhibits no stable fixed point. It's a 6-dimensional order parameter. I think we calculated with one of my students, but its phase diagrams show very interesting curves where you have the two regimes separated by a tricritical point. You really see that you have the possibility to have a second order transition curve because you have the crossing between the first and the second order transition regime. And so you cannot say it could be first order. You really see the transition going from first to second order. And so here you don't have a stable fixed point. So here, what can we say? So let's say conclude this part first. So no definite rule can be inferred from the existence of absence of stable fixed point. It works in most cases, but not always. And you have some strong counter examples. Now, more general conclusion to conclude my talk. So there is, I remind, a remarkable agreement for the critical exponent for elastic, proper ferroelastic transition, systematic disagreement of the experimental value with expected non-classical exponent, beta smaller, alpha larger, as if replication play a more important role. Now, the conjecture relating the thermodynamic order with the existence of a stable fixed point, well, it's contradicted by all order parameters smaller than 3 because you have a stable fixed point and you can not say more about the order. But for n larger than or equal to 4, then it seems not to be so bad, but it has to be, let's say, confirmed. Now, I want to conclude really, because I did not understood until now why you are interested by structural transition, whereas in magnetic phase transition, where you have very nice, let's say, symmetries, you have only to add time reversal symmetry. The number of space group go from 230 to 1,600, but it's the same, let's say, order of magnitude. And you have there density of second order transition, which is much larger than for, let's say, structural phase transition. And more in addition, the mechanisms are much better understood because you know the nature of the interaction. You see, you have exchange, how to say, relativistic interaction. You know what are the interactions which are at the origin of the anti-ferromagnetic phase transition. You have exactly the same. So, okay, I mean, it's not, how to say, my business to push you to work on magnetic phase transition, but it's a field which seems to me much more adapted to the fact of now, do fluctuation play an important role? I don't know that. You see, this is a field which is not my field. Now, what I want also to say about the fact that I would like that magnetic phase, or also liquid crystal phase transition, it's, let's say, structural phase transition on its soft matter, that we have beautiful second order phase transition in liquid crystal, not in complex fluids, but in liquid crystal. So liquid crystal is also domain, and we don't have so many type of phase transition, pneumatic, smectic, and so on. And you have change in the dimensionality, much more of the system, much more, let's say, common than in structural phase transition. And also, I want to insist again, I plan initially, it's in the program which I have sent, to speak about the role of defects, but I found out that it was not really useful. But you see, we have uncontrollable factors in structural transition. Structural transition, it's a class where you have many possibility of coupling of the order parameter with many type of quantity, including defects. So they are much more difficult to handle theoretically than magnetic phase transition. Okay, thank you. All right, is there some question, please?
May I?
Yes, please, please.
Yes. I strongly disagree with your statement about the possibility of having second order transitions with no stable fixed point. Can you elaborate on a specific example in which that happens?
Yes, I gave just now the case of boracite, nickel iodine boracite.
Yeah, but what is exactly observed?
Second order transition, this is true. It goes from cubic to monoclinic. What is observed? Well, the transition goes really as a second order phase transition, and the order parameter has 6 dimensions. I have calculated the possibility of having a stable fixed point. There was no stable fixed point. And this is all what I can say at the time where I worked on.
What are the exponents that are observed experimentally?
I have to see. I never tried to go and see the because it's a transition which occur at around 40 Kelvin, and it was mainly known for its magnetostructural property. I mean, it's how this called this effect where magnetism and the polarization occur in the same time. Let's say, okay, I don't remember the effect, magnetoelectric effect. It's a magnetoelectric compound that was mainly studied for its magnetoelectric property, not for the critical exponent.
So my attitude would be that the fluctuations in this material are probably relatively weak, and therefore to see the crossing to a first order transition, you have to go very, very close to the transition. In all your tables, you had a temperature range of the order of 10 to the -1, that's much too large for seeing real critical phenomena. The statement of no stable fixed point is that if you go sufficiently close to the transition, it will turn first order. That's very difficult to see experimentally always, because it's very difficult to get so close to the transition.
Yes,
But, theoretically, there should be no exception to that rule.
I perfectly agree, not with your conclusion, but with the fact that effectively there is nothing proved about the fact that you have first order or second order, because of, if you admit that the critical region is so small that it's almost unobservable. So you can always say that if you go sufficiently close, it is first order. Yes, of course.
Yes, I will show such an example tomorrow.
Okay, thank you.
But there could be also a different explanation of this experiment, is that when we say no stable fixed point, this is not a waterproof statement. It just means that people did the renormalization group in 4 minus epsilon dimensions, and in 4 minus epsilon dimensions, they haven't seen a stable fixed point.
All right.
But the actual experiments are done in 3 dimensions, and it might well be possible that in 3 dimensions there exists a stable fixed point which is not connected continuously to 4 minus epsilon dimensions, and then there's no contradiction.
All right. No, I mean, I know that people working with, let's say, fluctuation with the renormalization group or its extension are convinced that this is a real, that this statement that a second order transition requires a stable fixed point. I know that they believe in that. Only since I am not from this, let's say, community, I can have a, let's say, possible critical view about that.
No, but Pierre, you have not really proved that there is no stable fixed point, because you didn't do the calculation in 3D. You did the calculation in 4 minus epsilon d, right?
Yes, yes.
So it might still be the case. The fact that we believe that in 3D there should be stable fixed point, this is, I think, has a higher degree of validity than the belief that every fixed point in 3D should somehow be connected to 4 minus epsilon.
Okay, okay,
So,
okay.
I think there is no contradiction. I mean, rather, it might be what Amnon says, that fluctuations are weak and then there's no contradiction, or it might be more interestingly that
no, you see,
yeah.
I have no, let's say, prejudice.
No, it's very interesting.
So I have no prejudice. Only is that my feeling during all the period where I have tried to look in this critical exponent story was that we were still, let's say, needing a theory of critical exponent. That what had been done was not enough. This was my feeling, that theory of critical exponent was still to be elaborated, perhaps in a more accurate or more complete way. This was a feeling, and this is why I did not try to work in this field, because it was I was not able to do it.
We also have this feeling, so that's why we have our program.
Pierre, I would appreciate if you can send me references to these materials which have second order transitions.
Okay, it was studied by Hans Schmidt. As you know, he was the father of this multiferroic story. When I was in his laboratory, I spent 1 year with him in Geneva, and he studied all nickel iodine boracite. And this one, nickel iodine and all the other boracite, it was the only one with a real second order phase transition. All the other ones were first order.
So if you find the references, please.
Yes, yes, of course.
Thank you.
And also I have to mention that, how to say, There was a paper by a student of Dialoginski on nucleodyne Boras, who is Yuri Gufan. He worked and gave argument, but I shall send you. I'm not all the reference. By the way, they are in my book, the Landau theory.
Any further questions?
No, please.
Maybe
I shall repeat your question.
yeah. So maybe I would ask one question on.
Yes, please.
Still on the acoustic phonon. So so basically, I understood that this work of Larkin and Pekin showed change between second order to first order behavior, but would it be possible that even in a second order transition, the acoustic phonon would lead to a change of scaling indices in some way? Because so these acoustic phonons, they are massless, so they propagate stress at large distances. So they cannot, I don't know, it's just an idea. In a way, they are critical because they don't have a correlation length. So one might wonder if they could have some effect on the second order phase transition as well.
Yes, well, the paper deserved to be mentioned because it was the first paper where really they tried to show what type of correction could be brought when you take into account some elastic degree of freedom.
Okay, yes. But
I think actually, Achille, I'm very interested in this question. If you know anything about it, if you studied the paper of Larkin and Pekin, then we might have a discussion about that. But
I just looked at it.
There were many papers after that paper. The leading paper is by Bergman and Halperin.
Yeah, there are many important papers, but what can we? Yeah, it would be nice to indeed appreciate this point.
I don't actually know much.
But Slava, I want to address your question about the ferroelectric uniaxial materials. When the ordering is ferroelectric and the interaction is dipole-dipole interaction, then it changes the propagator at q equals 0 in Fourier space. And that is why all those systems are shifted from the upper critical dimension of 4 down to the upper critical dimension of 3, and they have logarithmic corrections. However, if you have an anti-ferroelectric order parameter, then the action is not at q equals 0, the action is at q equals pi, pi, pi. And at that point, the dipolar interaction behaves nicely, and therefore the propagator is practically the same as for short-range interactions.
That's
so the difference is between ferro and between anti-ferro.
Okay, that is helpful. But can you make a similar explanation for the ferroelastic materials?
Well, I guess so, yes. Ferroelastic are also usually ferro, so they are the long-range dipolar interaction enters crucially, and that's why you have mean field-like exponents there. And if they are anti-ferro, then they won't.
Okay.
Okay, is there other, please?
There are a lot of second order confusion equal thing.
Yes.
Can you please repeat the question?
Yes, of course, I will repeat, but let him finish, please. Let him finish his question, then I shall repeat it.
So, there is no any theoretical effort to, for example, take in a sense way to show that this system, the upper critical dimension is instead of 4. I mean, because according to the rest, it's quite strong. No? I mean, like you have a equal.
Say yourself the question. Repeat. I don't know what
No, my question was, as we do equal free, we've seen a lot of agreement with the classical Landau exponents. I was wondering if there has been any theoretical trial, for example, to show in this system the upper critical dimension, which is defined as a dimension where the exponents are mean field theory, where the mean field theory works. In this case, is equal free.
I have no answer to that, so if there is somebody.
No, but I'm sorry, it's just what Amnon just said. Amnon Aharoni just explained that that he explained why for ferroelectrics and for ferroelastics, he explained that there are some long-range interactions that explain that the upper critical dimension is 3.
Okay, is there some other questions?
I wanted to mention, so you mentioned in your conclusions, you asked, why is it that we don't work on magnetic and liquid crystal transitions? So I can answer that. So in fact, I tried to look at the liquid crystal transitions and see if we could do anything about them, but I didn't really find interesting secondary transitions that we could do anything about. So maybe I looked badly, but for example,
let me then propose something for you, Slava.
Yeah, so if there's someone can propose, then I'm really very happy.
I have a series of papers with an experimental group at MIT that looked at the exotic phase transition. The order parameter of the exotic phase transition is an XY order parameter. However, in the measurement of the order parameter, they see all the averages. Okay, the complex order parameter, let's call it X plus IY. Okay, when you calculate the measurable quantities, you first raise X plus IY to the power N, and then you take the real part of this. Okay, so for N equals 2, for example, the real part of this is X squared minus Y squared. For N equals 3, the real part is X cubed minus 3 XY squared or something like that. That's the Potts order parameter. All the higher harmonics of the complex number give you different operators at different orders, and you have an infinite sequence of independent exponents describing each of those quantities, which you can surely calculate by bootstrap on the XY model.
But the universality class is just XY model in 3D. What is the universality class?
Pardon?
Is the universality class believed to be XY model in 3D?
For example, yes.
Okay, yeah, then we can compute those exponents, but this is already
what I did at the time was what I knew to do, namely the epsilon expansion for this.
Yeah,
so you can look at it in any dimension, but since you know to do things in 3 dimensions, then here is a list of infinite number of operators relevant and measurable in liquid crystals.
Yeah, okay, that's interesting. That's interesting, but I was wondering if there are, of course, we already know XY model in 3D and we studied, but I was wondering if there are some
these operators.
Also, these operators, maybe not all of them, but some at least of them have been studied, and I can send you references. But I was wondering if there are some, for example, phase transitions in liquid crystals, which are described by some CFTs, which we haven't been paying attention to yeah.
I don't know all the literature. There must
Yeah,
be.
that's the comment. And another comment is also, Pierre, you mentioned that why is it that we don't look at magnetic phase transitions? So the point is that we are, as a community, we are familiar with simple symmetries like ON group symmetry and things like that, and we are, we know of magnetic phase transitions with ferromagnetic phase transitions with simple order parameters like Ising, XY, and O3 model, and those we know very well and we study them. But we are not very knowledgeable, we are very ignorant about this more complicated antiferromagnetic phase transitions where there is an interplay between magnetic order and the crystal lattice. So those are those which have more complicated symmetries. As you mentioned, it's even more complicated than structural phase transitions. So, but in principle, yes, we would like to study also those. So I thought that structural phase transitions was the first class of phase transitions where the space groups of crystals start playing a role. But the moment we get this, we understand the space groups, yeah, we can go to more complicated magnetic phase transitions or anti-ferromagnetic phase transition. Yeah, if there is anything interesting there, yeah, that's also interests us.
Yes, I mentioned magnetic phase transition because first, the symmetry are not more complicated. You just have to add time reversal, and then you get everything. So it's only one symmetry operation, which is of course not a simple symmetry operation. It's not a space symmetry operation, but all the symmetry group and all this crystallographic, let's say, aspect of magnetic phase transition is very easy to handle. And I would need half an hour to open for you the field of magnetic symmetries. This is one point. Second point, what seems to me interesting in magnetic phase transition is that let's say, in contrast to structural phase transition, we know the nature of the interaction. We don't have, we know the interaction in magnetic phase transition. Relativistic exchange, you can explain much more easily. Thirdly, there is something very interesting in anti-ferromagnetic phase transition. The order parameter has a microscopic nature, let's say. It is a spin density wave. It's not a macroscopic quantity. I speak about anti-ferromagnet. And so it is and mainly you have a mine of second order phase transition. Magnetic phase transition are much more second order, let's say, than structural phase transition. So really, and also people from the renormalization group, let's say Amnon Aharoni, and let's say also David Mukamel, they study many times, I think so, magnetic phase transitions. And they give a number of examples of, let's say, stable fixed point, not stable fixed point. So really by concentrating on structural phase transition, you miss the possibility of finding the good argument that you are looking for. And I think it's nothing more from the point of difficulty to go to magnetic. Liquid crystal, it's another story. It's a very interesting story. And by the way, since it was mentioned, the exotic phases of, you asked me today a question in this, let's say, computer discussion, if I knew a phase transition where you have a 6-degree term, which is associated to a second order phase transition. In exotic, precisely the symmetry breaking term, it's a 6-degree term in the Landau expansion. You don't have a fourth degree. The fourth degree term is, let's say, isotropic. And you have to go to the sixth degree to have the possibility to break your symmetry. So this is an example that you can find in liquid crystal. You can also find it in structural phase transition. It will be more difficult. So I think that to enlarge to the field, which is not so large, of magnetic, structural, and liquid crystal, then you can really find all example or counter example that you need.
No, but that's great. I mean, we start with this. In fact, yeah, I'll be happy if you know, as a postscriptum to your introduction to of space groups, if David Mukamel or you gives us also half an hour postscriptum about magnetic phase transitions, or in our postscriptum about magnetic phase transitions.
Okay, I can send you at least a long list of second order phase transitions.
Yeah. I mean, that's because the barrier that we need to overcome is this barrier of space groups. Once we understand space groups, I think there are many things that we can do, as you tell us. We can do, and you're telling us that we should probably just go straight to this magnetic and not worry much about structure. Okay, we'll think a little bit about structural before going to magnetic. It's still fun.
Okay. I don't press you.
May I pick up on your earlier comment?
Yeah.
Is there any example in 3 dimensions where a conformal bootstrap found a new fixed point which does not exist in 4 minus epsilon dimension?
It's not to answer that, huh?
Yeah. No, there is no convincing. There's no 100% convincing example, but there are some conjectures that Andres Sturgeon will talk about, I think, tomorrow. He's going to give a talk about some puzzles in conformal bootstrap. So he has some candidates for these fixed points. I don't think there is a proof that it's not still waterproof, but there are some signs that such fixed points may exist.
Okay.
But I don't want to claim to make too strong claims.
It would be nice to see such an example.
Yeah, it would be nice to see such an example, but there are many conjectures fixed point of this kind in the literature. Okay, there are not in the conformal bootstrap literature, but there are some people in functional RG who claim that there are some fixed points which appear and at intermediate value of dimension. Like they don't exist near 4, but then they appear near 3.5, and they disappear again, and things like that. So in principle, it could happen, but I think it would be nice to get more rigorous control over these things.
Okay.
Sorry, use this because hear you.
So is there any question? I don't hear.
Kinks in the O of N bootstrap that some Fisher fixed point. Going to higher external dimensions reveals a new set of kinks, most of which have no explanation in the epsilon expansion as of now.
I'm sorry, Connor, the beginning of what you said got lost. Can you repeat? Sorry.
I just said that these aren't the standard kinks in the O of N bootstrap that agree with the Wilson-Fisher fixed point using a phi to the 4th interaction. There are additional kinks in the same allowed region if you just extend the range of the plot.
Yeah, so thanks for reminding us. So indeed, Amnon, you see, in this conformal bootstrap, we get excited when we see some kinks, but some of the kinks we see, they can be explained in terms of known fixed points like ON, but sometimes we see some kinks that we don't know how to explain in terms of known fixed points. And then we would like to speculate that perhaps there are some additional fixed points out there. But of course, it's not a proof. We have to like look more carefully at those kinks and see if indeed it's fixed points and not just some junk. So it's kind of work in progress. So, yeah.
We are in the time to stop, but if you want to continue,
I was just not I was not rushing the discussion. It's good to have a discussion, not just but I think we are going, probably it's a good moment to thank Pierre Toledano for this nice series of lectures.
thank you.
So I'm going to stop the recording and see everyone tomorrow.